um ano ainda, né?
Obrigado, obrigado.
Você veio correndo, maratona?
Não, porque eu fiz caminhei, mas está muito calor. Então,
Vamos começar.
Me confundi.
Good morning, everyone. This is the last day of the workshop, and we start with Xi Wen from Chinese Academy of Science at Wuhan. Xi Wen, can you hear me? Xi Wen? I see your pointer, but I do not hear you. Are your microphone on? I do not hear you. Xiwen, probably you want to check your microphone. Can you hear Xiwen, Angela? Angela does not hear you as well. I hear something, not. Well, yeah, Chiwen, I see you moving your pointer, but I do not hear from you. Can you check your microphone, please? I think he can hear because he removed his.
A conexão dele que tá ruim lá, por isso que não tá aparecendo. Eu também tô com fechado lá.
Tá. Xiwen, can you say something? Saverio, a message appears here with saying that the sound is not activated. Maybe Obrigado. Pasquale, are you online? Pasquale, can you hear me? Xiwen, how about you log out from Zoom and then log in again?
Yes.
Oh, now I hear you. Can you say something? Not hearing you anymore? Since the world is not so wide connected.
Hi, everybody. Can you hear me?
Hi, Pasquale.
Yes. Hi. Morning.
Morning.
How about we switch between Pasquale and
If you
Xiwen?
want, while you understand what is going on, we can switch with Siwen and I can talk first and Siwen second.
Okay. So, Pasquale, can you share your screen and we see if your presentation.
But now I don't hear the people in the room.
I can hear
but can you hear me?
But I'm also live.
Buongiorno.
Hello?
Oh, buonasera. Can you, Pasquale, can you share your screen? Can you hear me, Pasquale? Parece que ele não consegue ouvir a gente.
Ciao, Angela. I can hear you.
Ah, you can hear. Can you share your screen?
So how are you? How are things? Are you in Italy?
Yes, I'm in Italy. I'm in a conference in Rome right now. So
See.
I took a break, come to make talk.
You make two conference in the same day.
Saverio, eu acho que ele não está ouvindo a gente. Eu acho que ele não ouve a gente.
Could manage to come to Brazil.
No, okay, it was too
Pasquale,
complicated.
can you hear me, Pasquale?
Yes, I can hear you.
Can you share your screen, please?
Yes, sure. I can share. Can you see it?
Yes.
Yes.
Okay, maybe switch between Pasquale and Xiwen while Xiwen sorts out his technical problems. Pasquale, please, go ahead.
Okay. So first of all, I apologize for not being there, but okay, I was very busy this week and with some institutional meeting in the first part of the week, and now I'm in a conference in Rome, so it was really too much to fit in even the Brazilian school and workshop that I'm sure is going wonderfully. But okay,
然后
I
最后一
want
个
to,
人在讲了，
没关系了，你的
我
I explain, now we can hear you, but I start the talk.
高一点。
不是
Xiwen, we are exchanging. Pasquale go first and you go second, okay?
OK
Sorry for that.
我上去之后，
Go ahead, Pasquale.
你现在不用讲的话，你可以跟我先试一下。
啊，
Okay, may I continue? When can you move? Okay, perfect. So I wish to wish Chico happy birthday. 70 years is an important number. And okay, to celebrate this happening, I will report on some new phenomenon that we found that we call the quantum Bemba effect, which has been studied through the lens of a new introduced quantity, which we call entanglement asymmetry. The work I will present is joined with Filiberto Ares, that is postdoc in CISA, and Sara Murciano, which was a former student in CISA, and now she's postdoc at Caltech. Okay, so what is the classical Bemba effect? But probably it's better to go in this way. What is the classical Bemba effect? is the very controversial, counterintuitive, and bizarre phenomenon that hot water can freeze faster than cold water. Okay? This is a completely counterintuitive effect that, honestly, when I discovered it, I was really surprised about this fact. And I was even more surprised to know why it doesn't move. Okay? That actually was known to ancient Greek already. In fact, Aristotle, in one of his was writing that to cool hot water quickly, begin by putting it in the sun. Okay? But this phenomenon stayed completely in the shade for many years until it was rediscovered thanks to the ice cream making by an African kid called Mbemba, which he rediscovered in the 60s. Actually, there is a very nice anecdote of how he discovered through ice cream, but the time that we have here is too short for me to go through telling this anecdote. But okay, what one can observe when freezing water is what you can see in these graphs here. That if you put hot water, the red curve in the freezer, the temperature of the water as measured in some quite peculiar way, it drops down, you see, then it stays around 0 degrees for a while because it has to freeze. Okay, so this is the coexistence phase of water and ice. And then it continues decreasing in the ice phase. The same thing happened for a warm water, like taken at 18 degrees, that is room temperature, let's say, okay? And the very bizarre fact is, you see that the departure from the coexisting phase of the hot water, the one that was starting at 45 degrees, is much faster than the departure from the freezing, from the coexistent phase of the warm water, the one that was starting at 18 degrees Celsius. Okay, this is completely counterintuitive. I hope that you recognize this fact, and was completely unexpected to me. Actually, since it's a very simple phenomenon, it got a lot of advertisement also on the press. Here I report on some newspaper that just in the recent few years, like 1 or 2 years old, all these articles were discussing about the Mbemba effect. Okay, and you see also the ice cream that changed the physics, the controversy continue over the whether hot water freezes faster than cold, and very similar title, even in Italian, actually. In Italian news, you can find about this effect. And in fact, it says that it's a phenomenon observed long ago and a difficult problem for physicists, and everything was born from an ice cream in Tanzania. Okay. But as we say, this is very much controversial. What it's believed nowadays is that this phenomenon is not relating at all for freezing. It's just freezing is just a particular case of the statement that hot system can cool faster than colder one. And these appear in many different experiments. Actually, there is a very nice experiment that was published in Nature 3 years ago, based on colloidal system. Colloidal systems are soft matter systems that are a lot controllable, are a bit like the cold atoms. Everything can be taken under control in a proper manner. Okay? And by the way, can someone tell me when I have 5 minutes left? Because like that, since there is no feedback from the room, I'm really a bit detached. Okay, so this colloidal system provides a very controlled setting in which Mbemba effect can be quantitatively described. In particular, since one can access the position of the single particle at any time, one can define a distance between the state at time t and the equilibrium state at low temperature, okay? And by studying this distance, one can understand the Mbemba effect properly. For example, here I report the results of one experiment in which this distance is studied from an hot system, okay, that you see it has some distance larger than 1 from the equilibrium state, and some warm system which is at lower temperature, and you see that the distance from equilibrium is smaller compared to this one. But as the time passes, you see that the hot system get to equilibrium before the warm one, because the two curve corresponding to the distances cross it at some point. Okay, so a signature of the Mbemba effect is that the curve for the distances between hot and warm system cross, exactly like the temperature was crossing in this graph here. Okay, it's the same thing. And in this experiment published on Nature 3 years ago, the authors considered several different initial conditions, several different parameters of the colloidal system. And as you see, in most of the cases, there is a crossing, okay, detecting the presence of the Mbemba effect, but in some cases there is not. So we can say that while nowadays it's clear that Mbemba effect exists and is valid in some circumstances, the condition under which this takes place are still not completely clear, okay? And this is probably the source of many past controversial results. But I don't want to discuss the classical Mbemba effect. I want, I like quantum mechanics, so I want to study what happens in a quantum mechanical system, okay? But quantum mechanics is really too big field. Let's focus on some system. What we have in mind here is an isolated quantum system at zero temperature, prepared in a non-equilibrium pure state. Okay, exactly what we do in a quantum quench. And as you know, as we discussed in many talks before this conference also, such a system relaxes locally to a Gibbs ensemble in the case the system is ergodic, or to a generalized Gibbs ensemble in the case the system is integrable. But what does it mean that it relaxes locally? It means that the reduced density matrix rho A of t tends to the equilibrium 1, okay? So the limit for large time of the reduced density matrix exists, and we can call rho A infinity, and it's equal to the reduced density matrix of the Gibbs ensemble, or generalized Gibbs in case of integrable system. So the fact that the relaxation is local suggests that a quantum Mbemba effect should be defined at the level of subsystem, not at the level of system, okay? And about all possible quantum system out of equilibrium, we focus here on initial state that break asymmetry of the Hamiltonian, which is symmetry of the Hamiltonian. And such symmetry is eventually restored by the time evolution, by simply Melvin-Wagner type of argument. If we thermalize for large time, we cannot have spontaneous symmetry breaking in a thermal system at in one dimension at finite temperature. Okay, neither continuous, neither nor discrete symmetry. Just there cannot be any symmetry breaking in one dimension at finite temperature. Okay, and the same is expected also for the generalized Gibbs ensemble in the case the charges are in involution. Okay, but now what we need is an experimental measurable quantity that tells us how much asymmetry is broken at the level of an arbitrary subsystem. And this will lead to the definition of the entanglement asymmetry, which I will provide soon. I check the time. So what is the basic setup? We have a quantum system, think to a spin chain, okay? We can construct the density matrix of the system as the projector on that state, and we focus on a subsystem A made up of a number of spins, okay? The charge Q that we consider is a local charge generating a U1 symmetry, for example, the magnetization along the quantization axis that we choose to be in the Z direction. Now, if the state is symmetric, the the density matrix, the total density matrix commutes with the charge. So by taking the trace over the environment, B, also the reduced density matrix commute with the reduced charges, which means that the reduced density metric as a block diagonal form, each block corresponding to a given value of the charge within the subsystem. Okay, so the total charge of the system is fixed, but each subsystem can have a different value of the charge. This decomposition can be written as a direct sum in this way, and this naturally leads to the concept of symmetry resolved entanglement, which is a subject that Chico pioneered 4 years ago with a very seminal paper on the subject. But here I will not discuss about symmetry resolved entanglement. Okay, I want to describe the case when the symmetry is broken. Okay, so what happens when the symmetry is broken? Now the full density matrix does commute with the charge, and so does the reduced density matrix, which means that the reduced density matrix is not block diagonal. There are elements outside the diagonal, these blocks. And what we do with these elements outside the block? Okay, one thing that we can do, we can erase all the elements outside the matrix and build another density matrix, rho AQ, which is constructed from the previous one by canceling all the off-diagonal terms. This is just can be obtained by summing over all the projection on the matrix on the various symmetry sector. Okay, so in practice you can imagine we cancel this element, and mathematically this is obtained by making this operation here. Okay, having defined this two density matrix, reduced density matrix, we can have what we call the entanglement asymmetry, which is the difference between the von Neumann entropy, which I recall is defined as minus trace rho log rho. So the von Neumann entropy of the density matrix where we erase the off-diagonal term, and the entanglement entropy of the real density matrix. This quantity can be proved by definition that is greater or equal than 0 because it's a relative entropy. And this makes sense because by canceling element out of the diagonal, we remove some coherence, and removing some coherence will lead to a higher entropy state. Okay, just physically make very much sense. And it's 0 only if the two matrices are equal, which means that our rho A is already in block diagonal form, which means that there is symmetry. Okay, so this entanglement asymmetry is a proper measure of how much the symmetry is broken. Okay, but how we can access it in analytic and numerical work? Through a replica trick, which we also introduce in this paper, which just tell us that instead of considering the von Neumann entropy, we can consider the difference of Rényi entropies now, which are the log of the moments of the this reduced density matrix. And then by studying this object for integer n, which is easier, one can eventually take the limit for n that goes to 1 to obtain the von Neumann entropy, exactly like we do for the normal entanglement entropy. Okay, but how this object can be accessed? Okay, so the idea is to write the projector in its Fourier transform like written here, and in this way the matrix where we cancel all the elements can be written as the integral of rho A sandwiched between two vertex operator-like object e to the minus I alpha QA e to the I alpha QA. Now, if we have to build the moment of this matrix, okay, that's what enters here, because what enters here is just the standard Rényi entropy that we know how to compute. If we have to build the moment of this matrix, we have n integrals over alpha of what? Okay, so we have n integral over alpha of some object that we call generalized charge moments. Generalized because generalized the charge moment introduced by Chico in his paper with Hermann and Xavier. And these generalized charge moments are just obtained by multiplying this n of this object. Okay, so you see that here there are one after the other n of this object. But now, since rho A and QA do not commute, we cannot just commute this object and put all on one side. We should keep the order. Here, the orders matter as a difference for the symmetry resolved case. Okay? I hope it's clear. This will be the only technical slide of my talk. All the rest will be very easy and worthy. So let's us start understanding this entanglement asymmetry in some simple case. Let's take a ferromagnet, for example. The charge ferromagnet align in the direction of quantization QZ. In this case, the state commute with the charge, which means that the asymmetry is 0. That's fine. But now we tilt the ferromagnet, okay? Which means it's a ferromagnet in a direction which is a angle theta compared to the quantization axis Z. Okay, one can compute the entanglement asymmetry. It's just a simple exercise of quantum mechanics. Since state is a product state, it's very easy. Okay, and one obtains this nice compact formula that, okay, probably seen like that tells little, but can be studied and can be plotted to be understood better. For L equal 10, for example, we see that in the limit n that goes to 1, this is a monotonic function between 0 and pi over 2, and then it's symmetric and it decreases to pi again. Okay? So there is no symmetry breaking at pi at theta equal to 0, which is the ferromagnetic state, the one of the previous slide. And then the symmetry is broken more and more as we tilt these spins here, and it's maximally broken when the spins are perpendicular to the z direction, okay, which is here, and then slightly they come back by symmetry to the, obviously this curve should be symmetric by around pi over 2. And interesting observation is that one can take the largest limit of this formula, finding that the entanglement asymmetry scales always like 1/2 log L, but notice that the limit theta that goes to 0 and L that goes to infinity do not commute. Okay, so now that we understood this state, we can use this state as the initial condition for our time evolution. Okay, that's exactly what we want to do. So for studying the asymmetry after a quench and having something like a quantum Bemba effect, okay, what we want to do is to start from the tilted ferromagnet that break the symmetry, okay, let it evolve like with the free fermion Hamiltonian given by the XX spin chain, okay, which restore the symmetry because this object is symmetric as possessed U1 symmetry around the quantization axis. And then one should make a lot of algebra to compute the charged moment I introduced before. Okay, you can see that for the experts, this charged moment has the right form compatible with the quasi-particle picture. You see here the standard signature of quasi-particle picture. But okay, I don't want to enter in now we made this calculation. Just we have this final result that is very compact, and we confront it with numerical data, and we see that the charge moments works very well. But the charge moments are just an auxiliary object to get the entanglement asymmetry. Let's move immediately to the entanglement asymmetry. These are the results for the entanglement asymmetry. Okay? What we observe from these curves here. First of all, the entanglement asymmetry tends to 0 for large time. As we know, the symmetry is restored. So this is a signature that for large time, the symmetry is restored. Okay, and actually, if you are interested, one can find a very nice compact formula for the entanglement asymmetry at large time, and find that the entanglement asymmetry decay to 0 as 1 over t cube. Okay, so it's restored even quite fast, algebraically, but with a large power. Okay, the second thing that we learn from this presence of L here is that the obvious and expected fact that larger subsystems require more time to recover the symmetry. But okay, I want to move to the strange phenomenon that appear and is evident in this graph, the fact that the more the symmetry is broken, you see this red curve compared to the blue and to the green, the faster the symmetry is restored. Okay? You see that these curves crosses, all crosses, okay? And so the symmetry is maximally broken in the red case and minimally broken in this picture for the red one, for the green one. But we see that for large time, they go exactly in the opposite order. And the symmetry is restored actually faster for when it was more broken, okay? And this effect, we call it the quantum Bemba effect. For analogy with the classical case, you remember that it was the crossing in the classical case of the distances between the equilibrium state. Here instead we have a crossing of the entanglement asymmetry. Okay, so even in quantum system, the more the system is out of equilibrium, the faster the equilibrium is recovered, as measured by this entanglement asymmetry at level of asymmetry. Okay, but one can wonder, you made the calculation just for free fermion. Does it have anything to do with reality? Okay, it's just free fermion. Okay, to show this, we studied the robustness of quantum Bemba effect with respect to interaction, integrable, and also to non-integrable interaction that appear as second, next neighbor interaction. Okay, and we see here that in these plots there are several cases of non-zero delta, non-zero delta 2, periodic and open boundary conditions. So we really explored a bit of all the possible cases, and we see in these curves that there is a crossing between the entanglement asymmetry. Okay, these are exact diagonalization data, so our finite system. And being finite system, we have recurrence, so the large time limit are, these objects here are not at all important, they are just recurrence. But at short time where the system is still the same as an infinite one, we see crossing of all these curves, showing that quantum Bemba effect is really robust against integrable and non-integrable interaction. Okay? I hope this is convincing for you. How much time do I have still? Hello?
How about 5 minutes?
5 minutes, okay. In the remaining 5 minutes, then I want to present a recent enterprise that we took with the experimentalist in Innsbruck, okay, led by Christian Ross, okay, and to show how quantum Bemba effect that I just showed can be seen in trapped ion experiment. Okay, the protocol that we do experimentally is the same that we did in our theory before, which was prepare the system in a tilted ferromagnet, okay, exactly like before, and then quench it to the Hamiltonian of the trapped ions, which is an XY model with long-range interaction. Okay, this interaction decay like 1/2 to the R cube, and they are exactly known. This is what the Hamiltonian of the trapped ion, and see that this Hamiltonian is symmetric as the U1 symmetry. So we are exactly in the same condition of before. By using the procedure called randomized measurement and then classical shadow formalism, one can estimate the entanglement asymmetry, the replicated one actually. Okay, I will not enter in how to make this measurement because this really time is short and isolate from the scope of the talk. So what we do, we analyze in this experiment, first of all, the theta dependence in the initial state. You see that there is this bell-shaped result that I already showed you for the theory case. And here you see that the experiment, which are the dots here, completely match the previous formula. The continuous line is exactly the formula I gave you before. Okay, so these results certify that initial state preparation is good. And then we make the time evolution with this Hamiltonian, and okay, what we found in this case is we studied a system of 12 ions. Okay, we consider, here I plot just what happened for a subsystem of 4 ions, but the same consideration are valid for small and that larger subsystem. And you see that the second entanglement asymmetry, the second Rayleigh entanglement asymmetry, are shown here the experimental data, which are the dots, the symbols, against the theory data of the, but theory now is exact numerics in the presence of the small dissipation that is within the system. And you see that theory and experiment agree perfectly, and not only, they both show the crossing, which are signature of quantum Bemba effect. Okay, so we can say that the quantum Bemba effect has been seen in trapped ion experiment. These are still unpublished results. Soon we'll write up the paper and show this very nice result. And actually, I can quickly discuss curiosity, which is the effect of dephasing. Okay, the system of interest has a very small dephasing. Okay, of the order of 1, which is here. And in these plots here, I plot the unitary dynamics, which are the full lines and are the same in the 3 plots, against the theory with some dephasing. Okay, if the dephasing is small 1, like in the experiment, you see that these are the dashed line. The phasing results are very close to the unitary 1, and actually in the short time regime, they are basically negligible, and you see very clearly the quantum Bemba effect. If you start increasing the dephasing, you see that now there is a larger departure from unitary dynamics, as expected, but there is still the quantum Bemba effect. If you go to the limit of very strong dephasing, this is basically gamma equal 100, means pure dephasing. It's one particle, it becomes one particle physics. You see there is complete departure from unitary dynamics, as expected, but also the curve here, they crosses very nicely, okay? And there is quantum Bemba effect even for pure dephasing, okay? And actually, the crossing happened even before. In some sense, we can say that dephasing makes Bemba effect stronger. Okay, so I think since the time is short, I don't want to discuss the case of non-symmetry restoration, okay, because I want to leave some time for some questions. So I want to conclude by saying that we introduce a new experimentally accessible quantity, the entanglement asymmetry, that actually has been already measured, okay, which measures the symmetry breaking, and this new quantity allowed us to discover a new unexpected phenomenon, the quantum Bemba effect. Obviously, what we have done till now, since this quantity has been introduced only a few months ago, is just the tip of the iceberg of what it can be done, and we are working in these directions. So some of the current research directions are entanglement asymmetry in ground state, the breaking of non-abelian symmetry, what happened in random unitary circuits and integrable models, and last but not least, what happened for disorder model, in particular in the many-body localized phase. And okay, I will conclude here with I would appreciate some questions if possible. And I want to finish by saying happy birthday to Chico, and thank you for having me here, although only remotely.
Thank you, Pasquale. Okay, questions, comments? Yes.
Can I make a question? So very nice talk.
Go
I have
ahead.
2 questions. You mentioned here in the conclusions, can you tell a bit more what you have studied, what happens when integrability is broken in principle? You showed some integrable examples, so.
No, I show some non-integrable.
Yeah.
Where it is. There is not, integrability doesn't matter so much.
Doesn't matter, yeah.
You see, these are the integrable, 2 integrable cases. These are non-integrable cases. Okay, the only difference is that one system thermalized, the other not.
Pasquale, you're not sharing your screen anymore.
Oh, sorry. No, here it says that I'm sharing the screen. Can you see it?
No, we are just seeing you.
That's strange, because here it says you are screen sharing.
Just a
I can
second.
stop sharing. Now I stopped sharing, and now I can try to share again. Do you see now?
Just a second. Since that's our end. Now, yes. Thanks.
Okay, so you see these two top panel are the integrable case, the bottom panel are non-integrable case, and the physics is basically the same.
So,
Eduardo?
so then you expect something different because you put in the conclusions that you want to study more the integrable cases, or you?
No, I won't. Okay, these are just numerical calculation for the interval cases. What we want to do is to derive analytical formula for the interval case that should be possible.
I see.
Okay.
I have a
Eduardo,
second, just quick
let me
question.
take question from the audience here, please. Eduardo, please go.
Okay. Thanks for this beautiful talk. The question I have is, do you have an intuitive hand-waving argument that explains this unintuitive effect?
I would love to have, but I don't. And the same is happening in classical physics, actually. There have been proposed for classical Mbemba effect some intuitive argument, but they apply to very limited case, okay? And there is still not a general an intuitive argument that explain why the Mbemba effect classical happen. And okay, now making directly, we are really, these are the first results on this counterintuitive effect. Probably we should first understand in which circumstances it will happen, how general it is, and then maybe we can try to draw some conclusion and physical effect. However, if any of you has idea, I'm willing to discuss, and I would really love to explain physically what is going on and what is happened, but for the moment it's just an evidence. Experimental and theoretical evidence, but not more than that.
Great, thank you.
More questions?
Yes.
Wait a second,
please,
Angela. It's Chico now.
Okay.
Hello, Pasquale.
Ciao, Chico.
Oh, ciao.
Hi, just a minute. Can you just say some words about the trapped ion experiment that you mentioned? You have no time.
Okay, go ahead.
No, okay, more than what I say, this is it's a trapped ion experiment with 12 ions interacting with the long-range XX Hamiltonian here that has U1 symmetry, and then one perform. Okay, discussing the randomized measurement will take a full talk and not some time, so really I cannot. Would be really long to discuss, and I don't know even if I have the right expertise to discuss how the randomized measurements are performed in the experiment. But is this the main keyword is randomized measurement to extract the entanglement asymmetry.
Which ions, which temperatures, or
temperature is the effect of the temperature is together with the dephasing that you see is very small. So basically, there is the preparation of this the state here, and the temperature is negligible for all practical effect. It can be encoded in this small dephasing that is in the system, and that's all. And the ions, I don't remember which one they are. Sorry.
Chico.
Hi, Pasquale. Pasquale, this reminds me, in the old times, the problem the people has in metallurgy. How they produce the good combination of iron and carbon to do steel. And exactly happens these things. You start to cool. At a certain point, sometimes it's much better you heat again and then cool because of, some sort of the evolution goes to some, they are trapped in some place. And then they produce it's much more quick, not so that, and the quality also is much better if you do that. That's what I do. Combination of this annealing, the annealing, that's so that they could go. So this reminded me something like that also here. No, I mean the
yes, this is actually on these lines. Is what it has been proposed for the classical Mbemba effect in some cases, that, it's like having you have to reach some minimum, but if you go upper in temperature, you can escape some valley and then go to the minimum that you are interested faster. That's basically what happened in, at least my understanding is what happened in metallurgy, and could be one of the explanations for the classical Bemba effect. And probably it is a bit what is going on, but still it's a bit of rephrasing of the model. Not and now we know when this happened then. Okay, when is it convenient to make this ramp up and then go down, and when it's not. The argument doesn't explain. It's a bit like saying, it's again another experimental evidence with, but it doesn't give a simple physical argument why this thing is happening. But yes, you are right. My impression is that the two things are related.
Thanks, Pasquale, for this very interesting talk. I have unfortunately to move on, so let's thank the speaker again.
I will stop share the screening to give the words to Xiwen.
Xiwen, can you hear me? Xiwen? Good,
Yes.
I can hear you. Can you share your screen,
Okay,
please?
can you hear me?
Yes,
No.
loud and clear.
Okay, let's try again. My friend helped me. I just re-log in, and now I just using the share. Just using the share screen. Okay, then I click on this.
Yes, all is fine.
So
Okay.
far, so good.
Please, go on.
Okay, now it's okay, looks. Can you hear me?
Yes, yes, please, go on, start.
Okay, thank you. Okay, 师兄，谢谢你。Okay, good morning in Brazil. First, I would like to thank the organizer giving me this opportunity to present our recent work. I'm also very, very sorry for this accident because in China we using different system for meeting, and I also would like to say happy birthday to Professor Akaras. I first time met Professor Akaras in 1999 when I was a postdoc at the University Federal of San Carlos. Although I did not work directly with him, he showed me kindness, which made my life enjoyable in San Carlos. I truly appreciate it. Later, I met Professor Akaras several times at the international conferences. In particular, I invited him to attend a workshop in Wuhan in 2013. Here is him. In China, there is two most liked characters. One called Fu, means happiness. Another called Shu, longevity. There's a very beautiful poem for birthday. The meaning of this poem, 富入灯海，寿比南山, it means may your happiness be as boundless as the eastern seas, and your life as long as the long-lasting southern mountains. Wish Professor Akaras happy birthday and good health. The outline of my talk is the following. In the first part, I will introduce fundamental concept and the theoretical result on the spin charge separation phenomena, also the exact result of Yang-Gordon model. In the second part, I report the observation of the spin charge separation. The last part remains the concluding remark. The two references for this talk. As we know, the spin-charge separation is a very established concept. Unlike three-dimensional metal, whose low energy physics is fermionic quasi-particle. In one-dimensional interaction fermion, the low energy excitation are collective bosonic spin and charge density wave that disperse linearly as described by Latent Liquid theory. In this sense, there are three important features for spin-charge separation. One is the collective motion of the boson. Two is the sound wave propagate with different velocity. Three, the correlation function satisfy the homologous latent liquid theory. Although there are some nice papers already report the evidence for spin-charge separation, however, no one of them fully determine the spin-charge separation in terms of latent liquid theory. There are also many theoretical papers for making proposal for observation of the spin-charge separation. For example, in 2003, the author proposed to excite spin and charge wave packet in the ultra-cold atom trapped by harmonic potential. However, this proposal does not work. I will tell you why so far no one experiment certainly proved the spin-charge separation theory. In 2020, there is a paper. They reported evidence for spin-charge separation. They loading the fermion atomic in one-dimensional lattice. Then they drop the one fermion atom, like this cartoon showed. Then lead to the dynamic evolution of a single holon plus the spin dynamics. In this experiment, they claimed they found the holon propagate with a certain velocity. The spin configuration also propagate along different, with different velocities. However, I would like to see this experimental test is not really a spin-charge separation in terms of latent liquid. Why? Let us recall the phase diagram of the one-dimensional Hubbard model. They, in fact, realize the one-dimensional fermionic Hubbard model. In the repulsive regime, this model has 5 phases. Due to the time, I do not have enough time to explain every phases of the one-dimensional Hubbard model. I just mentioned the phase 4 is partially filled, partially polarized. Phase 5 is the half filled, partially polarized. It's a moot phase. You change the chemical potential, the density doesn't change. B is the magnetic field. What the experimenter observed is around this point. They just observed the dynamics of the single hole around this point. At this point, we check the holon excitation just like a single particle feature. It's not really a collective motion of boson. Second, the spinon dynamics is just given by the Heisenberg spin chain. So the dynamics of charge and the spin are outside the latent liquid region. We cannot see this is the real spin-charge separation theory of latent liquid. We found the good candidate for observe the spin-charge separation in terms of latent liquid is the Young-Gordon model, i.e. the one-dimensional atomic fermion gas. the Hamiltonian described by this form, this second quantized form, phi j plus is a correction operator from an atom at position x with the spin j. Spin j can be equal up and down. The second term is the contact interaction. Due to the fermion statistic, only the fermion with different spin state has interaction. The third term is the effective magnetic field, change the particle number at different spin state. This model now can be realized through the ultra-cold atom. The interaction strength can be tuned through the confinement-induced resonance. The strength can be tuned from negative infinity to the positive infinity. If the G negative, they call it attractive interaction. They has a ferromagnetic ordering in spin sector. If G greater than zero, it's antiferromagnetic ordering. This model, in fact, already was solved a long time ago in 1967 by Professor Xian Yang and Golden. In recent years, we have spent a lot of time on this model and find the model has rich physics. In this talk, merely involve the last three recent papers. Now let me explain you how to use this model to determinately observe the spin charge separation. As we know, the wave function for this model is basis-like. It's the superposition of the plane wave with the amplitude can be determined by the wave number Kj. The wave number Kj satisfies the transcendental equation coupled to the spin rapidity lambda. Those equation, in fact, is very complicated because they have the complex root form the spin stream, i.e. the bound state of spinor. For the macroscopic property, we have to use the grand canonical ensemble. From the base answers, we can determine the macroscopic state, EI. Then we can write down the partition function in terms of the EI and with the degeneracy WI in terms of the base answers root. By minimizing the Gibbs free energy, then we can get the equation of state. The pressure is dependent on the dressed energy of the charge, the charge degree. The epsilon k is like the single particle dispersion subject to the spin fluctuation. Spin fluctuation is characterized by the dressed energy of the spin stream bound state phi n with n spinor bound state. Those infinitely many nonlinear integral equations lead to a big problem, a difficulty for solving this kind of equation. However, we can develop some analytical technique to solve this equation in different region, physical region. For the phase diagram, because if we want to measure spin charge separation, we must determine in which region is suitable for experimental setting. So in this phase diagram, we in the chemical potential and the magnetic field plane, we using the dimensionless ratio, Wilson ratio, which is the ratio between the sensibility over heat divided by temperature. For certain temperature, we can find this ratio in certain region is constant. For example, in this region is equal 1, is fully polarized phase. In this region, partially polarized phase, this ratio is a certain number, which is independent of the temperature. The spin charge separation is most subtle shown for experimental measurement, because if we choose a wrong region, it's out of the experimental capability. So we find for h equal 0 along this trajectory is really good. We can have analytical result and also experimental control is available. Now let's ask the temperature. In which temperature regime we can measure the spin charge separation? Because all the experiments is carried out in finite temperature. So that's why we should also determine a suitable temperature regime. This is the temperature. The horizontal is the chemical potential. For fixed magnetic field, then at 0 temperature, we have a phase transition from the partially polarized phase to the full polarized. At the critical chemical potential mu c, then the phase transition occurs. And at finite temperature, for example, we can counterplot the specific heat. Then the specific heat indicates the energy fluctuation. The maximum of the specific heat fan out from the critical point, form the critical region. Then we can get analytical formula, scaling form of the specific heat. From this scaling form, we can read off the critical exponent, dynamic critical exponent, Z equal to correlation length exponent is equal half. However, below the dashed line, this is the true latent liquid phase. In this phase, the system keep in linear dispersion. So in this linear dispersion regime, then the specific heat can be given in terms of the sound velocity Vc and the spin velocity Vs. And the effective Hamiltonian for the latent liquid can be given by the standard canonical Boson field, the momentum pi and the phi and the phase. This is the very standard Tomonaga latent Gaussian field theory. If we consider the temperature greater than the spin excitation energy, less than the Fermi energy, this regime is too hot for spin degree of freedom, but is still cooled for charge degree of freedom. In this regime, we find the heat has two terms. The first term is linear T dependent. The second term is cubic. This indicates more or less of liquid and the gas coexistent. The correlation function, for example, the single particle correlation function, showed the spin correlation is exponentially decay. However, the correlation in charge degree is still power law decay. This regime called the spin incoherent liquid. Now we can confirm the spin charge separation. The best regime is in this region, in the Latent Liquid regime. For example, H equals 0, we can find the sound velocity, the charge sound velocity going to the Fermi velocity. The spin velocity goes to 0 when the interaction strength increase. So that's what we want to find this nature. If through increasing the interaction strength, find the opposite tendency for the spin velocity. To understand the spin charge separation, we have to go to the low energy excitation. For in fact, we know this model has a very complicated excitation spectrum. However, for very low energy excitation, the dominant feature is the particle hole excitation in charge degree of freedom. This green color shows the particle hole excitation in charge degree of freedom. This form a continuum spectra. However, for the momentum very small, equal h bar delta k, it's very small. They give the linear dispersion with a quadratic correction. Quadratic correction is give the curvature correction. This curvature correction is also important for realistic experimental observation of the dynamic correlation function. So we also know how to get the effective mass through the dressed energy and the Bezier equation. For spin excitation, the dominant spin excitation is the two spinor spectrum. Like flipping one spin lead to two spinor. This spinor excitation spectrum can be given by this form. Small momentum give the linear dispersion with the cubic correction. It turns out this cubic correction is not important in low energy excitation. The important feature for spin degree of freedom is the backward scattering. This involves the dimension 3 marginally operator. So at low energy physics, this figure is standard linear latent liquid with the linear dispersion. This is what we need to understand the dynamic understand of the dynamic correlation function. We have to consider the curvature correction in charge degree of freedom, the backward scattering in spin degree of freedom. So the Hamiltonian should describe by 3 parts. Let me explain to you the 3 parts. The first part is the linear part, HC and HS. This is the Gaussian free field theory plus a sine Gaussian type. This is related to the dimension 3 operators, marginal operators. In order to further make a connection between Bezier and the personalization, we have to know some characters. For example, charges, latent parameters, spin latent parameter, and velocity, and phase stiffness. We get those quantity through the Bezier equation. Summarize the useful result for comparison between the theory and experimental result. As we know, the dynamic structure factor for charge and spin by latent liquid prediction is delta type. Okay, this is the dynamic structure factor, the imaginary part of the response function. However, as I mentioned, we need to consider the curvature correction for the chart degree of freedom. So the dynamic structure for realistic experiment need this form. This is the response function, and this response function given by free Fermi distribution with the effective mass and the curvature correction, Q plus and minus, indicate two threshold value. And the spin dynamic structure factor can be calculated using some known result. Here we calculate the spin dynamic structure factor for low temperature given by this formula. This is the closed form. It's very useful. And this form subject to the safe energy, which is determined by the renormalization constant by this formula. Tf is the Fermi free energy, Fermi temperature. T is the temperature. This is the theoretical part. However, how to measure the spin charge separation, the dynamic structure factor? That's really a hard problem for experiments. Fortunately, recently the development, in particular the advances in control the ultra-cooled atom, provides such an opportunity. Using the Bragg spectroscopy can measure the charge and spin dynamic correlation of the atomic system as a function of excitation energy omega through the two photon Raman process. Like this figure, shining a pair of the Bragg beam on the 1D tube. Then the system received the photon excited to the excited state, and simultaneously emit the photon to another ground state. Then lead to the momentum transfer equal K1 minus K2. And experimenter can using the time flight to capture the linear density of the alt-carbon atom. The alt-carbon atom is the caked atom by the Bragg beams. That's the due to the time restriction, I cannot explain in detail how the experimental to determine the transfer of the momentum. This is just a trick, the experimental trick. Probably I should spend some time to explain how can make the experimental observation connect to the spin and charge density view. Through the Bragg perturbation, the Hamiltonian can be given by the perturbed Hamiltonian given by this formula, this form. The Bragg beam coupled to the spin state. Then experimentally can tune the light shift potential. Sorry. And to the detune from spin state, this parameter, then they can make the transfer momentum directly proportional to the response function. For example, the density correlation given by this nothing but is the charge density view correlation. And also the ZZ response function, this nothing but is the spin density view correlation function. Those correlation function we can make directly connect to what we obtained through the personalization result. Okay. Okay. This cartoon picture shows how experimental to adjust the detuning for excite spin excitation and charge excitation separately. While in previous experimental measurement cannot measure the latent liquid nature in their experiment, because usually they expect simultaneously to observe the spin density wave and charge density wave. This cannot happen in ultra-cooled atom because the spin excitation and the charge excitation has different scaling, quite different scaling. So we have to keep the same condition for the system, separately excite spin excitation and charge excitation. To this end, then they using the lowest two hyperfine state of the lithium for the spin half interacting fermions. Then they using the 2p state as excited state. Then they sending the Bragg beam to excite the atom to the 2p state. Then from the 2 speed through the 2 photon process, then they can measure the momentum transfer. This momentum transfer just proportional to hc. hc is given by this formula. You can see this formula with the plus. Because we have the spectral function have up, down, up, because it has U2 symmetry, then we have up, and up, down. And the plus, this formula, the plus, just equal the previous density, charge density wave per correlation function. For the spin state, they have to use many experimental technique, try to reduce the rate of spontaneous emission in spin excitation. They using the hyperfine state 1 and 3. The purpose for this, they try to reduce the spontaneous emission. And also they using the 3p state as excited state. Then they using the 1 and 3 as the hyperfine state, I mean the spin up, up and down state with the 3p excited state. Then they perform the Bragg spectroscopy. Then they find the delta up, the detuning equal minus delta down. Because in this case, the delta S, the delta S comparable with the energy difference between the two spin states. So this means the spin up, spin down can feel different in this detuning. So that's the trick. They can measure the transferred momentum proportional to the SS. This SS is nothing but is the spin wave density correlation function. Okay. Once we know this connection, then we can calculate the experimental signal. Experimental trap associated of the tubes. The number in each tube can be fixed by the Gaussian distribution. So for us, we just want to know the numbers, the atomic numbers in each tube. Then we using this number, we can calculate the density distribution in each tube. Using the local density approximation in one tube, then we can know in small interval the dynamic structure factor. Theoretical tell us, for example, in very small interval, the dynamic structure factor looks like the blue. In one tube, it looks like the red color form a peak, a sharp peak. If we sum up all the tubes, the dynamic structure factor, all the tubes, then they give the round peak. So we using this tool, then we can compare our theoretical prediction result with the experimental data. Experimental for the spin dynamic structure factor, i.e., the spin Bragg signal is given by the square, by the symbols for different interactive strengths. The two interactive strengths for 0 per radius is non-interacting case. Then for 100, 200, 300, 500 per radius, then the interaction repulsion increase. They give different Bragg signal. Then we using the Fermion dynamic structure factor with the we using the spin dynamic structure factor with backward scattering give the solid line. This solid line really agree with the experimental signal. If we don't consider the backward scattering, then given by this dashed line. This dashed line obvious has a big discrepancy with the experimental data. This means we really need to consider the nonlinear effect in the Tomonaga latent liquid theory, given by this formula, by this effective field theory. So the momentum is just the keep a constant in each measurement. For example, the red dashed line, if we keep the momentum, transfer the momentum, then we measure the Bragg signal for different interaction strengths. Okay. Similarly, in charged Bragg signal, given which is given by the symbol theoretical prediction given by the solid line. The solid line is the dynamic structure factor with the bad curvature correction. So both theoretical and experimental data agree quite well. If we don't consider the curvature correction, then there big discrepancy. We can say obvious there exists a discrepancy. So that means the nonlinear latent liquid is really important for the experimental measurement at the final temperature. Here the temperature is 250 nanokelvin. So that's the formula we used for theoretical simulation of the Bragg signal. Okay, and also we keep the same momentum transfer. And for measuring the signals, spin and charge Bragg signal, they always keep the particle number is the same. The distribution is the same. So this means they keep the same condition for the spin excitation and the charge excitation. So they really map out this excitation phase diagram, this excitation spectrum. If we put together the spin and the charge excitation, we can see the peak of the charge dynamic structure factor and the spin dynamic structure factor move in different direction. The charge move to the high frequency part, you can see move to the left when the interaction increase. The spin Bragg signal move to the low frequency direction. So from the peak of the Bragg signal, we can get the sound velocity for charge and spin. The signal, okay, the symbols give is the experimental data. The dashed line is the theoretical curve. So we can see the charge velocity increase when we increasing the interaction strength. The spin velocity is decrease. This really agree with the theoretical prediction. Quantitatively agreement has been observed. Okay. Now is my concluding remark. We have presented rigorous result of the spin charge separation in the one-dimensional fermion case. Using the Bragg spectroscopy to directly excite either spin or charge density wave, we have observed that the velocity of the spin and charge excitation shift in opposite direction with increasing interaction. Also, the dynamic structure factor agree quite well with the Bragg signal. We have found the effect of nonlinear latent liquid resulting from the band curvature and backward scattering. It is a paradigmatic example of quantum many-body physics. Our results offer new insight into the quantum technology. For example, this providing promising way for measuring quantum feature information. For example, we can also measure the dynamic structure for the attractive Young-Gordon model, which will provide the signature of FLO pairing correlation. Also, through this technique, we can measure the quantum feature information. That's what we are have been doing in this topic with experimental collaborators. My collaborators, with the Professor Randy Hulit group, experimental group at Rice University, and Han is the direction from the Rice University, and Ya-Ting Chang is the postdoc. Oh, sorry, PhD student of Randy Hulit. He Feng used to be my PhD student. Now he's a postdoc working with Professor Masato at CISA. Wang Sheng also just graduated in the end of last year. Now moved to the Hong Kong University for the postdoc study. Thank you very much, and wish you a happiness, prosperity, and success in the year of rabbit. Thank you so much for your patience.
Thank you a lot. Thanks, Shiwan. Questions?
Hello.
Hello.
You showed very careful experimental and theoretical comparisons for the latent liquid theory for the spin and charge velocity and how they depend on band curvature, interactions, and so on. And it's very careful and beautiful work. But as you mentioned at the beginning, for me, spin charge separation in one-dimensional latent liquids means that the fermionic excitation is unstable towards disintegrating into spin and charge bosons. And I think this correct me if I'm wrong, but if this kind of experiment shows the bosonic excitations, but the ideal situation would be to inject a fermion and to see it disintegrate into the spin boson and the charge boson. Do you think that is feasible with this kind of systems or not?
Yeah, thank you so much for your comment and also your very technical question. Because the temperature very low, so I mean the temperature very low and the momentum is very small. The transfer the momentum very low, so we do not need to consider very complicated high order coupling between the charge and the spin. So we just consider the bosonic mode plus marginally correction in curvature and also in the backward. For other correction, is related to the more than dimension 3.
But my doubt is whether you can inject a fermion, create a fermion, a bare fermion in the system, and then observe this fermion disintegrating into a spin mode and a charge mode. So it's not just observing the spin mode and the charge mode with all the corrections and interactions and so on, but to see how a fermion, a bare fermion, disintegrates into two bosons. Do you think that kind of experiment has been done, can be done?
I'm not so sure about that point. I'm so sorry that.
No problem.
That probably here we just found evidence for the nonlinear correction, the nonlinear effect, rather than in very detail how other type of fermionic contribution.
Okay.
We really only examine if we consider this curvature correction and the backward gradient, that has a good improvement.
Any more questions? Well, we are running late. Let's thank Shivan again. Thanks, Shivan.
Thank you.
Have a good night. And
yeah, apologize to all of you again for the accident. Here also very late. I'm sorry I will miss the following talks. I have to go home to take care of my daughter. And thank you.
Hello, everyone. Let's start the last session of this morning with Professor Ronald Dickman from Minas Gerais. Does it work?
Well, agora sim. Okay. Have to wait for Chico. No? Wait for Chico. After all, here he comes.
Now you can start.
Okay, I'll wait for everyone to come in. Okay. Good morning, and many thanks to the organizers and Chico for the invitation. I'm going to talk about non-equilibrium systems in a kind of study that goes back to the 1980s. I should apologize. I'm not a mathematical physicist or a condensed matter physicist. Sometimes I say I'm a condensed metaphysicist, because I typically work on models that don't exist in the real world. So that's metaphysics, if you like. But there is a connection with Chico that has to do with directed percolation and quantum spin chains that he analyzed along with his collaborators so beautifully some decades ago. So that's, I suppose, the connection. But I've always been very happy with Chico's interest in what I'm doing. So I hope that you'll find something interesting in this seminar, and maybe a challenge for understanding what's going on. We'll come back to this film later. We've heard about lattice gases yesterday. Where is my talk? Here it is. Is this it? Full screen. Okay, I think this is it. I have so many versions, I might have taken the wrong version. Okay, so here we have a large cast of characters. Which I'm going to talk about these Witten-Rawlinson systems, principally the driven Witten-Rawlinson system. And my collaborators on that part of the work are Royce Zia and Max Labrintovich, Ig Chate, and my PhD student who's here, Guilherme Oliveira. There are 2 papers out. This is the original report, and then this is more theoretical attempts to find a field theoretic description that are still in progress. So what's the Witten-Rawlinson model and extensions thereof? Paradoxically, it involves the idea that opposites repel. So how to arrange that in the laboratory isn't completely obvious, but maybe some trickery with polymer brushes on colloids would work. Anyway, I'm going to talk about phase separation in equilibrium, which was the original motivation for the Witten-Rawlinson model. And then we'll go to what happens under a drive. I'll make a brief review of another driven system, the driven lattice gas with attractive interactions to give a certain contrast. And then if there's time, I'll talk a little bit about random sequential adsorption and percolation. But maybe in the interest of time, I'll skip that or go very quickly. Let's see. So the original Whittem-Rawlinson model is a continuous space model of a fluid, a two-component fluid, in which there's no interaction at all between the molecules belonging to the same component. So we have, let's say, species A and B, no interactions between molecules of species A, no interaction between molecules of species B. But A and B have a hardcore repulsion. And the interesting thing about this model, even if it's somewhat unrealistic, is that Whittem and Rawlinson, in their original paper, were able to demonstrate rigorously that there is phase separation above a certain critical density, right? So at low density, you'll just have these A and B particles roaming around with the volume exclusion between A and B. But as you can imagine, when the density becomes high enough, or the chemical potential, if you like, it's going to be necessary to have a separation into A-rich and B-rich phases. And that's the unmixing or phase separation that Whittem and Rawlinson were able to establish. So as I say, continuous space and hard sphere excluded volume interactions between A and B pairs. It's worth noting that in all of these models that I'll be talking about that are athermal, there's no energy scale. So all of the ordering occurs due to entropy maximization. In other words, when the system is phase separated, which you might consider to be more ordered than a uniform mixture, it's because the entropy of the ordered phase is higher for those conditions than the disordered phase, which is not a completely new discovery, but it's always worth mentioning to break this notion that entropy is a measure of disorder. Sometimes, not always. Okay, so the first step in this saga was a work in collaboration with George Stell that was published in 1995, which is Whittem-Rawlinson lattice gas. So now we put the model on a lattice, square lattice, cubic lattice, and first of all, this idea that arbitrarily large numbers of A particles or B particles can sit on the same site wasn't very appealing, so we imposed site exclusion amongst the A and B. And in addition, an extended hardcore between A and B particles. So there's nearest neighbor exclusion between A and B particles. They cannot be nearest neighbors, but they can be second neighbors in the version that we study. And putting it on a lattice allowed for much more detailed simulations, allowing us to confirm via finite size scaling analyses that the model, the phase transition to A and B rich phases is Ising-like, as you would expect already on the basis of symmetry. So now I'm going to make a detour to another model that was very popular in the 1980s and 90s, which is the attractive nearest neighbor lattice gas, which has an energy function that we can write this way. Sigma 0 or 1 indicates an occupied or vacant site, 0 being, well, 0 is vacant, 1 is occupied. So it has an energy function that's very similar to the Ising model in zero external field. And in fact, this is mappable, precisely mappable onto the Ising model. So we know what the equilibrium critical behavior is. But the interest of this model in the mid-80s and thereafter was placing the model under a drive that favors hopping along a certain direction of the lattice and suppressing hopping in the opposite direction. In equilibrium, naturally, the system undergoes a phase transition analogous to the Ising critical point, separates into dense and rarefied phases. And we have a compact droplet, if you work in the canonical ensemble, and surfaces are generically rough. Sorry, in 2 dimensions. So, I jumped a lot. Okay, so here's what happens in equilibrium, kind of phase separation into a blob. And under a drive, what's the drive? We have an external field or influence that I'll designate by D that favors hopping along one direction. Let's see. Yeah, here's the expression for the acceptance probability of a hop, which you have to think of this as a kind of Monte Carlo dynamics. So we have this gas, this lattice gas, and we pick a particle at random, and we propose a hop with this vector delta x. And of course, if the particle is going to hop onto an occupied neighbor, that's rejected. But supposing that the target site is vacant, then we have delta E, the change in this attractive Ising-like interaction. And we also have this additional term in red, which is the non-equilibrium drive. D is a fixed vector with a modulus which will define the degree of non-equilibrium. And so you can see that it favors hopping along the same direction as this external drive. Now, it's important that the boundaries be periodic along this drive direction. If not, we simply have an equilibrium system in an external field, like a gravitational field, which, again, is not very remarkable. So here is the expression. Here's how the drive enters. And what Katz, Lebowitz, and Spohn found, they published the first paper on this, I think, in 1983, is that there's phase separation, as you might well expect, but that the geometry of the phase separation is quite different. Instead of having a blob, we have a stripe that's oriented along the direction of the drive. The interfaces are smooth. It's not so obvious in this image, but if you go to larger system sizes, you'll verify that the fluctuation in the interface is suppressed by this drive, which you can sort of see. If something is sticking out here, it will easily get swept away and rejoin the stripe somewhere else where it's more energetically favorable. So these are the key points about the driven lattice gas with attractive interactions. Now, what happens, we go back to the Witten-Rawlinson lattice gas, and we apply a drive of a similar kind. Here's how the drive is defined in this case. There's no temperature scale for the Witten-Rawlinson model, so it's better just to work with hopping probabilities, and the drive will be along this direction once again. And you can see, if you look at the details, here we have a 1 plus P, here we have a 1 minus P. P is the drive intensity in this case. So these three transitions, these three hopping transitions, including second neighbor hopping, that have a positive projection along the drive direction are favored, whereas these three are suppressed. If you let P equal 1, these three are completely prohibited, and you just have these transitions. A is the second parameter that has to do with hopping perpendicular to the drive, and if we set A equal to 0, as I will in much of this discussion, then you only have these three possibilities. It's a bit like a totally antisymmetric exclusion process, except that we're in 2 dimensions. So here's what happens.
Relation invariance directly with the D factor, the first. I mean, you give a direction, a precise direction.
That's
to
right.
the other model.
Yeah.
And
So
the other one, you allows also to drive a little, not exactly on in one direction, but you allow also to go up with this.
oh, here too. Here as well.
Yeah,
In the driven lattice gas, because delta x could point perpendicular to the drive, and then there's no energy cost or work cost. But yeah, if you don't have hopping, at least with a component perpendicular to the drive, you're really stuck in one dimension, and then the physics changes.
You never give the separation, I understand. But the second example, what you do, you go up, here.
In this example.
Yeah.
These three are treated equally, and we also have if A is different from 0, we also have the possibility of going directly perpendicular. But even if you set A equal to 0, you still have hops with a perpendicular component, so you get to mix. Yeah.
You allow the cars in the lane
to change lanes. Yeah, exactly. Okay, so the big surprise was after knowing about phase separation in equilibrium, which is rather similar to what happens in the Ising model. The blue and black, obviously, are the 2 species, A and B. But what happens under a drive is something quite surprising. The system doesn't form one long stripe that wraps around, which certainly would minimize the interfacial area or length. It chooses to form these stripes. The stripes march through the system, as you may have seen on the video that I was showing. And there's a wavelength. The system spontaneously chooses a wavelength. This, if you look at the spacing or the wavelength for a complete cycle from blue to black, that's more or less independent of system size. It's a function of the density, of the drive strength, and also of that parameter A that I mentioned weakly. But essentially, we have a periodic non-equilibrium steady state. And of course, we'd like to understand why the system chooses a certain wavelength. That's part of what I would call open questions. Okay. So, do we need to see the video again? Did everyone see it? Maybe. Show it quickly. Okay, video is nice. I agree. Let's see. Yeah, this video may be more instructive now because first we're in the lab frame, so to speak. So you see a stripe going through. You see these little minority particles that are stuck for a long time. This video was made by, I believe, a master's student of Max Lavrentovich at the University of Tennessee. Now he's going to shift slowly into the co-moving frame with the stripes to make it easier to visualize the stripe dynamics. So you see there's a lot of defect dynamics. And eventually, most of the defects will disappear. Not all of them in this case, but you can see also that the interfacial undulations are highly correlated between stripes. So at this stage, we're trying to understand the basic pattern, but then there's a lot of work to be done understanding defect dynamics, roughness, undulations, how the undulations are correlated. Okay, I think that's enough of the video. Okay, so I've mentioned some of these surprises. Surprises if you're coming from the viewpoint of the driven attractive system. Otherwise, you might have no particular reason to be surprised by perpendicular stripes. Rough boundaries in this case, a preferred wavelength. And an important point is that even in the disordered phase, there's a preferred wavelength that you discover when you look at correlation functions. We can view this system, there's a background density, right? We're working with equal densities of A and B, although of course they can't be nearest neighbors. But we can look at the excess charge, which will be the difference between A and B in any given region, and also the excess density, right? The density is not completely uniform. So in the disordered phase, you still find modulations in the correlation function, the charge-charge correlation function. Remember, when I say charge, I'm talking about the difference in concentrations between A and B. So that charge-charge correlation function is periodic, but it decays. So it has an imaginary component to represent the decay in the Fourier representation, but in the ordered phase, or what we understand to be the ordered phase, at least ideally, there's a periodic non-decaying ordering. Okay. So here are just a few more examples of the patterns. For a given lattice size, when you get to a high enough density, there are only enough vacancies around to form two full interfaces. Remember, the interface has to consist of vacant sites, and then there are other vacant sites scattered around. You can get defect-free in the sense that every stripe is a complete periodic stripe that wraps around. We have periodic boundaries not only along the drive, but perpendicular to the drive. And here there are no defects, but there are still lots of excitations, let's say, undulations of the surface, slight variations in the thickness of each stripe. So there are lots of ways to disorder this pattern. The one question that mean field theory has been able to answer is the current. So some simple ideas about how particles are able to hop leads to this blue curve. And here's the comparison with simulation, so it's not too bad. But when you get to that single stripe regime, an even simpler expression that's familiar from the exclusion process fits the data better. Aside from that, mean field theory, even spatially dependent mean field theory, has not been useful in understanding this system. Let me show you one sequence that answers the question, why don't we have a stripe parallel to the drive, right? The drive is always pointing horizontally to the right. The reason, roughly speaking, is that if we start out the system in a nice horizontal drive, these interfacial fluctuations grow without any limit. There's nothing to hold them back. And eventually, they're going to wrap around this periodic direction and form vertical stripes. The vertical stripes, however, are not susceptible to this kind of instability. Okay, let me try to say something more quantitative about ordering. So we need an order parameter, and to define an order parameter, since we have a periodic pattern, we're going to look at Fourier amplitudes. So we'll look at Fourier amplitudes in correlation functions and in the distribution of the A and B particles. Here's a power spectrum, several power spectra, in fact, of different patterns. Here's one pattern at a high density, where you see M, which is the number of cycles around the periodic direction. M is 1, so that's the case where there's only one stripe in our notation. And then you see a nice Fourier series with the odd harmonics, as you might expect. So this is a very clean pattern. In other cases, still in the ordered phase, you see a Fourier spectrum, a power spectrum, with one dominating component. So we adopt the amplitude of the dominant component as our order parameter, duly normalized to the system size. And this shows you how the associated wavelength depends on density and also on drive strength. The ordered regime begins roughly around here, 6.5, 6.8. So this regime, as I say, we still can identify a wavelength, a preferred wavelength, but we're in the disordered phase. There won't be global coherence to this pattern. In fact, whether there's global coherence to the pattern in the infinite size limit is something that you might question, but we'll see about that later. Anyway, if we look at intermediate size systems, 100, 200 square, we look at this order parameter as I've just defined it, you see something that looks reminiscent of a continuous phase transition as you vary the density at fixed drive parameters. So it looks suggestive. But to get more quantitative results, we have to deal with a number of problems. We have a system size L that we can control, and drive parameters, obviously, and density. So our first idea was to fix the density, fix the drive parameters, and vary L and look at the steady state order parameter and try to apply finite size scaling, as you would in or out of equilibrium, to localize the critical parameter and optimistically estimate a critical exponent. But what happens in this case? You see these wild variations. That's because certain system sizes are simply not commensurate with a multiple of the wavelength that the system has chosen. So you have to be careful and study the envelope of this curve. These are the sizes L that maximize the order parameter, and they occur more or less periodically, as you would expect. So based on those measurements, we're only looking at the envelope of that curve, but looking at different system sizes and different densities, you get some curves that look reminiscent of subcritical, maybe critical maybe supercritical behavior of the order parameter, as you might see in the vicinity of a continuous phase transition. It becomes very difficult to study larger sizes at these high densities, mainly because of relaxation effects and fluctuation effects in the simulations. But we'd like to be able to extend and really see this stabilize as we increase L. Okay. So that's the story on ordering in this driven Whittem-Rawlinson lattice gas. I'll skip these slides. And let me say a couple of words about the disordered phase. Here's a typical configuration. You can see domains, perhaps, of majority black or white, but it's not really obvious that there's a wavelength associated, a wavelength along the drive direction. But if you look at the structure factor, it does become clear that the maximum in the structure factor is displaced from the origin, k equal to 0, along the drive direction. So there really is some favored wavelength. But, of course, as I said, there is no global ordering. So here are some further results showing details on the structure factor. There's also this kink. This is symmetric, of course, with respect to k and minus k. So there's a kink at k equals 0, which is a uniquely non-equilibrium effect. And there's this preferred wavelength or wave vector. Now, what can we say about theoretical description? Let me go to that. Royce Zia was in on this project almost since the beginning. What happened was one day I ran the simulations. I said, oh, the stripes are the wrong way. I better tell Royce. And of course, Royce, who spent decades working on the driven attractive lattice gas, was fascinated by that. And ever since then, we've been trading ideas. And a few years ago, he invited Max Lavrentovich, who is now at the University of Tennessee, to join in on this. And the first thing they did was apply a formalism called doi peliti, which is related to other formalisms like de Dimonisses or MSR, that lets you map a stochastic lattice model to a field theory with an effective action and all those nice things. So one of the key results from this analysis was that even under a drive, there are two velocities. There's a velocity for the density fluctuations and one for the charge fluctuations. I don't remember at the moment which is larger, but this appears to be behind the definition of a preferred wavelength. Okay. At the moment, Guilherme, who's here in the audience, there he is. Is working on numerical analysis as a prelude to full-scale renormalization group study of this. So just to give you an idea, I mean, here are the equations, but they're not very helpful. What you can see is that for the charge field, of course, there's a Laplacian, and there's a diffusion coefficient that's going to go negative in the phase-separated phase. That's standard. I mean, that more or less corresponds to the Kohn-Hilliard equation in equilibrium. And then there are various, there's a fourth derivative term that will prevent the system from having arbitrarily large wave vectors. This is the equation for the density, excess density, which accompanies And you see there are couplings, different nonlinear couplings between these two fields. So this is a key point that holds even in equilibrium. And the idea is to include the lowest order nonlinearities and see what this yields, and then go on and try to analyze the full equations. And of course, a complete description will involve Gaussian noise terms, a conserved noise in the case of the density to study fluctuations. So that's where we are at this point. These are the conclusions. I think I've mentioned all these things. And okay. As I mentioned briefly, the question of long-range order, even at high densities and high drives, is questionable because in equilibrium, you wouldn't expect that. We know of some active systems, like the VICSEC model, that managed to escape the Mermin-Wagner theorem because of non-equilibrium allows additional terms in the hydrodynamic equations, and one of them suppresses this instability, but it's not clear yet whether that will happen in this case. So that's also open. I'm going to skip this part and just mention that in collaboration with Bob Ziff and Paulo Martins, we're studying Witten-Rawlinson deposition, where you have random deposition, but you can't have A and B neighbors. And this leads to a percolation problem as well. But in the interest of time, I'll just say happy birthday. Thanks.
Thanks, Ron. Questions?
Just a quick and simple and naive question. If you do not include those hoppings in the vertical direction, just hoppings in the horizontal direction, does the instability from the horizontal to the vertical stripe happen?
We never looked at that, but let's see, you would expect, I mean, one row now knows nothing about the other rows, except perhaps for volume exclusion. We could maintain the volume exclusion. So I would expect that if you start out, let's say with a horizontal, with a vertical stripe, it will slowly dephase and there'll be nothing to avoid that. We never looked at this, I should say, but I'm just guessing. If you start with a horizontal.
Yeah, I was just wondering if that instability is driven by the vertical hoppings. Or
well, certainly the instability of the horizontal one is. I mean, we've seen some, but then we lose all the interesting physics. I think maybe we should look at that. Okay. It might be an easier case to understand.
Sorry, have you evaluated the roughness of the interface numerically and see how it diverges when you come to this critical point?
It looks like, what do you call it? Wilkinson.
KPZ?
No, it doesn't look like KPZ. It looks more like Wilkinson.
Edwards Wilkinson.
Edwards Wilkinson, yeah. From, our results aren't that precise, but the exponents seem to be EW.
Just a general question, because after all, you have defined your process, you have your very well defined, so you have your time operator who gives the evolution, so you have somehow a Hamiltonian, in this case two-dimensional.
Yeah.
So
an effective Lagrange.
If you write this Hamiltonian, they have couplings, whatever, and you have a phase diagram.
Well, almost, but we have some notion.
It may be difficult to find it. But somehow, if you analyze this phase diagram and you look for the ground state, that will be this steady state, maybe you can understand all the possibilities that you may have. Depends on the initial condition of your problem. You go one side or other side. Have you thought about this?
Well, we've thought about the Doi-Peliti kind of formalism, but not about a Hamiltonian in the sense of a spin chain and really looking at eigenvalues and all that. So who knows? Yeah.
Another question. When you say that you want to look for long-range order, but your pictures somehow show one order, which is what you mean by long-range in this sense.
I mean that the correlation function won't decay to zero. I jumped over, let's see if I can find this quickly. These, I mean, there's still an envelope here in this charge correlation function that may be decaying. And of course, this is a limited system size. It must be 160. So of course, it has to have a minimum at half the system size. The question is, what will happen in the thermodynamic limit? We don't know.
Okay, I have to move on. Thanks all again. Next speaker is Edson Dennis from Rio Claro, nearby.
Okay, this is yours.
Well, good morning. Thank you very much. First of all, I have to say I'm a professor of physics in São Paulo State University at the city of Rio Claro, so it's just 60 kilometers from here. I'm delighted to be here and thank the organizers for their invitation and wish Chico a happy birthday. So the title of my talk is A Phase Transition Characterized via Chaotic Diffusion for a Two-Dimensional Mapping. And the point I want to discuss is that I'm using a set of topics dealt in statistical mechanics to characterize a transition in a chaotic system. So I will then try to convince you and give a set of answers for a set of 4 questions. The first one, in a transition from integrability to non-integrability, I have to identify what symmetry is broken in a system, a candidate to an order parameter, and also to susceptibility, which gives the variation of the order parameter with respect to the counterparameter itself. And I want to discuss also what is the type of elementary excitation in the system, and finally discuss eventually what are the topological defects which impact in the transport of the particles in a chaotic dynamics. So to start with, I will consider this two-dimensional mapping. It came generically from 2 degrees of freedom Hamiltonian system, which is composed from an integral part H0 plus an integrable, a non-integrable one, which is controlled by a parameter epsilon. So because the Hamiltonian is time independent, so the energy is a constant, and we may reduce this 4D flux of solution into a system with 3D flux of solution. And then we intercept this 3D flux of solution by a plane, and the points crossing this plane defines what we call a surface of session, which is mostly described by a nonlinear mapping. And the mapping I decided to discuss today is written in terms of the same control parameter controlling the transition from integrability to non-integrability. There is a nonlinear function with a sign, and then there is a second dynamical variable, which is theta, which is modulated to pi. There is a 2 pi here on the right-hand side, which is covered by the figure. And the interesting thing is this function 1 over capital IN plus 1 to a power of gamma. So there is a set of 2 control parameters. One is epsilon, controlling the transition from integrability to non-integrability, which is clear. If epsilon is 0, we have IN plus 1 equals to IN, which is a constant, and together with the energy gives the second constant of motion. So we have integrability. And when epsilon is different from 0, and considering this capital I is small, and gamma is a non-negative parameter, any non-negative terms. It might be an integer, real, fraction, or any. If capital N is IN plus 1 is small, the ratio becomes large, and then this term added to theta n makes theta n plus 1 becomes uncorrelated to theta n because it's modulated to pi. And this loss of correlation makes this sign function behave like a pseudo-random number, and then we have the first equation describing a kind of random walk motion, random walk particle. And then we may see diffusion along this axis, which is mostly seen along of this phase space. So we have a parameter small, 10 to a power of minus 3. This set of points, black points here, identify a chaotic C, chaotic because if we measure the Lyapunov exponent, we see exponential separation from 2 different initial conditions. These regions on white regions define what is called KAM island, so we have periodic islands. And the 2 lines up there and down there are called invariant spanning curves. They are tori, which separate, which block the passage of particles on the chaotic C up or down there. So once we have an initial condition, a particle inside of this chaotic domain, it's still on the chaotic dynamics forever. So it could not enter a region of a KAM island, nor cross upper or down there. So a particle is confined here. So try to identify, and then when capital I becomes large, this radio no longer is large. It becomes well behaved, and then it brings correlation between theta n plus 1 and theta n. And we can see on the phase space this correlation mostly looking at the islands and on the invariant spanning curves. The red curves show only the first one, but we have an infinite set of them, either up or down there. So the first question to answer is an attempt to classify or identify the phase transition is to identify the broken symmetry. So we see if epsilon equals to 0, the phase space in the vertical we have action, on the horizontal we have theta, and the phase space is foliated. So if we give an initial action, it's still constant along this horizontal axis. And so the phase space is symmetric, and this symmetry is destroyed when epsilon is different from 0. So we see a break of symmetry in the phase space, and we can also see a break of symmetry, which is a kind of algebraic break of symmetry, because if epsilon equals to 0, the left-hand side is equal to the right-hand side. However, when epsilon is different from 0, this term perturbs in plus 1, makes the equation not symmetric anymore. So we have hints of the first answer to the first question. Identify the symmetry which is destroyed. So the phase space and either on algebraic. Let us move on. Try to describe or to give answer on the second question, which is a definition of the order parameter. So when we are working with chaotic dynamics, the first point we try to define is what is called Lyapunov exponent. Lyapunov exponent is a natural candidate to be an order parameter, but I will show you that for this case it is not a good candidate to be an order parameter, even though it defines chaotic dynamics whenever it is positive. So if we look at the positive Lyapunov exponent against epsilon, we see they are positive. So because the mapping is a 2D map, we have two Lyapunov exponent. One is positive and the other one is negative. And its summation is null, is 0, because it preserves the area on the phase space. So we are looking at only the positive Lyapunov exponent. So we see the error bar. They define the average along the convergence of the positive Lyapunov exponent over an ensemble of 5 different initial conditions. However, if we look at the horizontal axis, we see a massive variation of the counterparameter. It starts from 10 to a power of -6, ranging to 10 to a power of -2, plotted in a logarithmic scale. And we see that the positive Lyapunov varies very little, just from 1.7 to 1.5. It is about 15%, a variation very slow as compared to the massive variation. So the point I want to address is the positive Lyapunov exponent is not a good candidate to be an order parameter, because in a second order phase transition, the order parameter must go continuously to 0. At the same time, its susceptibility should diverge. And we see from this Lyapunov exponent that it is not tending to 0 in any case. So when we make epsilon different from 0, the phase space birth as mixed. And on the previous slide, we see that the upper curve limiting the chaotic diffusion it depends on epsilon to a power of 1/1 plus gamma, which can be calculated analytically from an approximation with the standard mapping at a very specific transition, a transition from locally to globally chaotic dynamics. So we can do this analytically. Then a candidate, so since we are looking at the diffusion, we look at the behavior of I root mean square. So we collect an initial action, we square it, makes an average over the orbit and an average over an ensemble of different initial conditions. And the behavior is shown on these curves here. So we see that for a short time they grow as a power law and eventually they bend towards a regime of saturation. And this kind of behavior here is described by an homogeneous and generalized function bringing to a set of critical exponents. For short, I will just say that for a long time, the I root mean squared saturates as a function of epsilon to a power of alpha. The regime of growth is a power law on n with a second critical exponent beta. And the crossover, which marks the regime of a changeover from growth to the saturation, depends on a third exponent z. There is a power law, a scaling law relating the 3 critical exponents, which I'm not discussing here. But here we have a candidate to be an order parameter. Since we are looking at the chaotic diffusion, a good candidate to be an order parameter is the saturation of the diffusion. So it's I sat, which scales as epsilon to a power of alpha. And alpha is a critical exponent which is always positive and smaller than 1. So we can calculate analytically as alpha 1 over 1 plus gamma. Gamma, just to remind you, is the exponent with hiding the term in the denominator of this equation, and gamma is a non-negative term, then alpha is always smaller than 1. However, non-negative. Nonetheless, when we derive this, all of these curves here can be described by probability density function. We can solve the diffusion equation, obtain the probability density function, which has a term which depends on the time, which is relaxation time, transient time, and then there is a stationary state. So this probability density function, it lies for our problem as the partition function lies for the statistical problem. So if we know the behavior of this function, we can determine all observables. So a good candidate to be an order parameter is ISAT, which goes continuously to 0. If we look at the behavior of the response of the order parameter against the control parameter itself, which is epsilon, it diverges, which is the derivative of I with respect to I, to epsilon, it diverges in the limit when epsilon goes to 0. So this seems to be a good candidate to be an order parameter. The third question we have to answer is the own elementary excitation. The chaotic diffusion only happens because we have this nonlinear term here, is epsilon sign, which works as step length for a particle moving in the chaotic dynamics. So the elementary excitation is the own nonlinear term. And finally, as probably is my last slide, the topological defects. Everybody knows that when you have chaotic diffusion in a Hamiltonian system, when a particle passes near this periodic island, there is a dynamical regime called stickiness, and the stickiness trapped a particle for a while. And then what these plots on the right-hand side show is what we define as survival probability a particle has to move inside a given region. So just to know what this survival probability is, we defined two stripes on the phase space and give an initial condition very close to 0 and allows the dynamics to run. When the particle escapes from this region, we stop the dynamic and give a nil initial condition. When the particle survives inside this region, it gives the survival probability. And far away from periodic regions, the survival probability is described by an exponential law. So we have here an exponential law, but eventually it reaches some periodic regions, and the periodic regions let the dynamics to experience stickiness. And the stickiness is marked by decay is lower than an exponential one. But if you look at the size of the number of particles which stay trapped inside of these regions is relatively small. So this gives us an evidence that the stickiness does indeed exist, but it does not affect the behavior discussed. So as a conclusion, we have studied a transition from integrability to non-integrability, and the observables allow us to conclude the transition observed is analogous to a continuous phase transition, as we see in statistical mechanics, since the order parameter goes continuously to 0, at the same time the susceptibility diverges. These results were published 2 years ago in EPL, and then thank you very much indeed.
Thanks, Edson, for this chaotic talk.
Maybe I missed your answer, but what is the symmetry that is broken?
Thank you very much for the questions. There are two symmetries we can expect. The first one is an algebraic. If we set epsilon equals to 0, In plus 1 is equal to In, which is the dynamical variable, which will look at the diffusion. So together with the energy, this constant I becomes the second constant of motion. It gives the condition to have integrability. So this is an algebraic break of symmetry. And the second one is the own phase space. If epsilon equals to 0, the phase space is foliated. So we see only parallel lines along the phase space. However, any epsilon different from 0, the phase space birth as mixed. So we have chaos, we have periodic islands, and a set of invariant spanning curves working as barriers, do not letting the particle to cross through.
So it's look like symmetry is big explicitly, right?
Yes.
Because you put the epsilon. It's
Yes.
not a spontaneous thing.
Yes.
Another question is, well, after all, when we say phase transitions, people always think in an infinite number of degrees. So you see some non-analytical behavior in the partition function in the case of statistical mechanics, and then your analogous here. You can say something, what we should do?
Well, that's a very good question, Chico. Thank you very much indeed. Let us have a look to the probability distribution function. So IFSC is, this term is, it corresponds to the stationary state, and this is only a transient because it depends on n. As far as n grows, this term disappears because there is an exponential, it dies exponentially, and then this term dominates. If we see here, we have IFSC on the denominator, and IFSC scales with epsilon to a power of 1 over 1 plus gamma. So this term here stays on the numerator. However, when epsilon goes to 0, IFSC diverges. So probably it also could be a hint on also this non-analyticity of the probability function, even though we don't have, but we have probability distribution obtained from analytically from the diffusion equation.
Very nice. Okay, I have to move on. Let's take Edson again.
Aqui a luz, aqui para frente, para trás, aqui nada, né? Tá.
Okay, last speaks of the session, Professor
So,
Lia do Amaral.
I'm going to speak about the problem of phase diagrams of complex aqueous systems varying concentration and temperature. So I start speaking something about Gibbs. So born in New Haven, prosperous and intellectual family. Enter Yale, 15 years, university prizes in mathematics and Latin soon later. Engineering PhD at age 24. His parents died. He plus 2 sisters became financially independent, and due to the health fragility, did not participate in the American Civil War. 3 years later, trip to Europe with sisters, age 27. He spent 1 year in Paris, 1 year in Berlin, 1 year in Heidelberg, connections with chemists and physicists. On his return to New Haven, he taught French for a time and worked privately on some of his engineering ideas. Then he was appointed Yale's first professor of mathematical physics. The role was unpaid, and Gibbs was happy with this situation. He needed not much money, and he was happy that the role required little teaching and allowing him more thinking and research time, quite similar to our professors. So let us look a bit at Gibbs' book, 902. It is in classical mechanics, before the beginning of quantum mechanics. And in his book, he really enters on chemical thermodynamics, modern statistical mechanics, and vector analysis, but also beginning of physical chemistry, study of multi-component systems. My interest here is to focus systems with different atoms in different molecules, trying to connect experimental results with available theories. So, chemical industry of soaps developed in the 19th century, and the concept of micelle was introduced in the 913. So let's see some basic knowledge in physical chemistry. Amphiphile are molecules with two parts with different polarities. Example, sodium dodecyl sulfate that has a paraffin chain and a polar head. And these, when you put in water, should be something, yeah. You arrive to critical micellar concentration, and this you must do experiments to define osmotic pressure, surface tension, equivalent conductivity. And then you get this CMC, and it is not a phase transition. So the micelle is a transient aggregate, looking a bit like that, but it is important to understand what's really going on. So you have the molecules, and then you have the hydrophobic effect that joins the paraffin, and the surface minimization. These two things together build the micelle by entropic factors. Now, let us remember that the chemical industries use tables to calculate enthalpy and entropy, all obtained experimentally. So these curves as a function of temperature belong to the engineering toolbox, and that was what Gibbs knew. So Gibbs studied multi-component systems, mixtures with N1 moles of species 1, N2 moles of species 2, etc., with corresponding chemical potentials 1, 2, etc. So I show now the group of physical chemistry working in Lund, Sweden. And that's a basic review paper showing ternary systems, ABC, at constant temperature, because chemists usually studied at constant temperature. And so that's the triangle they built. 100% A, 100% B, and 100% C, and here the weight percentages. So and then you have over 100 phase diagrams are shown in this reference of both binary and ternary systems, and the structure of each phase determined by X-ray diffraction. This was what it was known in the beginning of the 70s. Now, let us speak about lyotropic liquid crystal. That's my field for the last 50 years. So I just show here one slide I have presented in a recent paper in a conference in July, and I explain a little what's going on. So lyotropic systems, you have temperature here, concentration of amphiphile here, up to the critical micellar concentration, you have monomers in solution. Then in the isotropic, you have spherical micelles. They grow to hexagonal micelles. They grow to lamellar, bilamellar phases. And between hexagonal and lamellar, you have very complex cubic phases with minimal surfaces. But all these above the Kraft line that defines the order-disorder transition of the hydrocarbon chains. So below this line, you have gel and coagel, and only above this line, you have lyotropic liquid crystals. And many classify as biological and bio-inspired liquid crystals. So now we must speak a little about Lars Onsager. So he was born in Oslo, died in the United States. He also studied chemical engineering in Norway, but without a PhD. His inclinations were mainly intellectual, very good in mathematics, but with some difficulties in human communication. His interest in electrolytes was permanent, and he developed a deep appreciation of the relation between theory and experiment. So Onsager had a chemist's inductive point of view. And what did he do? He started correcting the Baeruekel theory of electrochemical equilibrium. Then he arrived to the famous reciprocal relations in irreversible processes, and then the solution of the Ising model in 2D that the physicists like so much. But I'm more focused in phase transition of cylinders with concentrations and effects of shape in the interaction of colloidal particles. And he worked also with thermal diffusion and turbulence. He got the Nobel in chemistry in '68. It was for reciprocal relations, but if you look, his Nobel lecture has nothing to do with that. His Nobel lecture is the motion of ions, principles and concepts, mentioning at the end H-bond chains and electrically active defects in water in connection to problems in biology. So, Onsager was a freshman chemist in the 20s in Trondheim in Norway and Zurich, where he was assistant of the BI, but emigrated to United States in '28. He got a formal PhD only in '35, pressed by university structure at Yale. In '42, during the war, I have arrived to minutes of the meeting of the American Physical Society, where he puts two abstracts, anisotropic solutions of colloids and of crystal statistics on more physical. The year '49 was Onsager's Annus Mirabilis. So he published the effects of shape on the interaction of colloidal particles. And in an appendix is about mutual excluded volume of two cylinders. And which are his references? His references are Langmuir and the DLVO theory of colloid stability. L is from Landau. The work of Lev Landau, Nobel Physics '62, in the 30s, included second-order transitions, but also the LVO theory of colloidal stability on interactions between colloidal particles and their aggregation number. So let us speak a little about phase transitions in liquid crystals. These are anisotropic molecules, and they could be analyzed as function of concentration with Onsager theory, and as a function of temperature with Landau theory. The crossing with lyotropic liquid crystals occurred with the discovery of nematic lyotropic phases by chemists, varying concentration, compound encounter ions by purely practical reasons. It was not academic work. And this was in '67. Now, I proposed the field of lyotropic liquid crystals at the Institute of Physics of USP in '74. And then I got my Freidocent degree in '82, all working in that. And I'm going to mention a specific paper I made a bit later on, where I discovered the nematic domain in this basic molecule that is the standard molecule for studies in biochemistry. But it was said that there was no nematic phase on that. But then I went and I found it together with this girl. And so this was published, and then I will explain a bit that I I used relative molar ratios instead of weight percent, because in a ternary system, weight percent means nothing. So we choose it, MW, that means the water amphiphile molar ratio, MD, decanol amphiphile molar ratios, and here is the phase diagram I got, temperature against this MD, and then clearly I have a cylindrical nematic phase, a discotic nematic phase, and a straight line without biaxial phase in the middle. And these results are for a fixed value of MW. So results indicate a change in micellar form at the NC and D transition. And physicists don't like that. They don't know how to treat a change in form. So let us look what happens in this ternary diagram at room temperature. So the nematic domain is this small point here. And it is between a big lamellar phase, an hexagonal region, and the isotropic region here. And here in more detail, the measurements I made. And clearly, I'm crossing this, and it's necessary that the object is changed. So there is something more here. Yeah, so that's the table that I could publish in this paper. I discovered a behavior unifying 3 amphiphiles with different properties. That's the sodium decyl sulfate that was everybody measuring, potassium laurate, everybody measuring, and the one I have measured, sodium dodecyl sulfate. You can see that potassium laurate and sodium dodecyl, they cross exactly at the same value of MD and very different values of MW. So for me, it was clear. I made an eureka. MD must be related to a change in micelle form, and MW must be related to the micelle size and intermicellar distance. So then let us look what was going on in theory about micelles. Charles Stanford made the basic theory. The theory is based on the separate estimation of the components of the free energy arising from hydrophobic attraction and from head group repulsion, each as a function of micelle size. And a bit later came this other basic paper by Israelashvili, 76, unifying geometrically micelles and bilayers. So he defines a surfactant packing parameter, that's the volume of the apolar moiety divided by hydrocarbon chain length and surface interface. And if this is smaller than 1/3, you get a sphere. If it is between 1/3 and 1/2, you get a cylinder. If it is 1, it is a flat bilayer. If it is higher than 1, it is an inverse structure. So then you could understand why detergents and lipids have so different critical micellar concentration, because detergents have only 1 hydrocarbon chain, they tend to be round, and lipids have 2 hydrocarbon chains, so they go in lamella. So then I looked and made another paper with with another collaborators. This was theoretical chemistry from Italy. And I had a student, and he had a student, and we have worked together. And then we noticed that the amphiphile has a P0 that tends to be curved, while decanol is tended to be flat. So we defined a mixed region is the ratio percentage decanol to amphiphile. Then analysis of micellar forms via elastic bending energy in terms of this surfactant parameter using differential geometry. So we could show that equations that made the change from spherocylinder to square tableted and as a function of this ratio. And so this solved the problem of the transition. But furthermore, we have agreement with experimental results in nematic and isotropic phases with X-ray by another group. So then I entered really to study lyotropic biaxial nematic phases. And so everybody was just looking to the only one that existed in the literature. It is this phase diagram from Salpi in 1980. And nobody could understand what was going on, and it is like that until today. So what I have made was a theoretical model together with Vera Enriquez that belongs to the group of IFSC. And then I proposed that let us really look a mixture cylinder disk and see why it does not decompose. And I proposed to look for different relaxation times for the micelle form transformation and micelle diffusion. So if you have enough time for the micelles to transform, then you enter in the biaxial phase. Otherwise, you have a direct transition. And so we could make these three theoretical lines from the microscopic model that I proposed. And the temperature effect is connected because there is chain construction only in the chain direction, but the volume does not change. So after this work, I have been invited to write a review paper only in the biaxial micelles, in the micelle, what's going on. This was published in 2010. And then after that, I started to look again experimentally to this system with another group of people. And then we arrived to show that there was at the same time one region of the phase diagram and with biaxiality, and another phase with phase coexistence of the two uniaxial forms. And this was published by a theoretician in 2016, and then he based it in our results. He produced this phase diagram with a big critical point where you have the biaxial phase, the two uniaxial phase, and the coexistent region, and he applies the Landau theory, but with another order parameter, not the usual one that the physicists used. So it is an order parameter connected to the concentration of the solvent and of the surfactant. And then this is in terms of number densities of surfactant and solvents respectively. And this paper has many phase diagrams that goes together also with what people from Maringá was doing. And so that's the scientific part of what I had to say. And I have one last slide only. Oh. Few things to say regarding connection with Francisco, that is the homage we made today. Oh my God. Well, oh. I was colleague of his brother, José Antônio, at Maria Antônia Fefecluspe in 59 to 62. And I worked at the reactor that's now IPEN for more than a decade. I got my master in 69 in nuclear science and technology, and a PhD in 72 in molecular physics at the Physics Institute. Francisco made master there in 77. I download now his master thesis. It's very funny. The content is different, but the formatting is very similar. The way something made at hand and the type is very similar. I crossed from Maria Antônia to reactor in 62, and I crossed from IEA to IFSC in 74, 76. And he crossed from IFSC to IEA in 75, 76. But we met really only today because he was a theoretician and I was considered an experimentalist. And my scientific connections with São Carlos started in '66 during the foundation of the Brazilian Physical Society, when I met Ivone. And then I worked with crystallography and so on. So coincidences of life, that's it.
Thanks, Nia, for this lovely talk. Comments, questions?
I remember around, I think it was 82, and people, show this last diagram that you're telling. In 82, it was, people did not know exactly what's the nature of this phase transition on liquid crystals. It's this critical point. And people at that time, we thought that maybe it's an example of what is called costly phase transition in 3 dimensions.
Não entendi nada, cara. Me traduz.
It's just a comment.
No, it's because besides everything, I don't hear with this ear and so only with this one. And when it's too loud, too many people
Don't worry, I will explain again to you. But anyhow, this was an old problem that theoreticians try to somehow to understand this in the scenario of some phenomena that happens in 1 + 1 dimension, but in 3 dimensions. And this will be the point where the people are looking for. But unfortunately, the problem was complicated, and then people invent other problems.
Yeah, and I like complicated problems because I am the only one that decides to go until the end and find an answer. And usually, I don't stay what it is fashionable. I have always looked because I thought like this. I am in an underdeveloped country. I am a woman. I must find something that nobody else is looking so that I can really say something about the problem. And so it was not easy because I was working at the same department with Salinas and the whole group of statistical mechanics and all the theoreticians. But I have made this paper with Vera Henriques more or less against the whole, because they don't accept that it can be different than what they want to be. So I decided to really enter, and then it was very interesting for me because I did not know this whole story I told today. I have learned this to make this because now it's clear that physical chemistry comes from Gibbs, and everything comes from this direction. But usually the theoreticians stay on the main line, the high road with high speed. And I like to go slowly. That's it.
Okay. It's good that we have people that stay slowly. Otherwise, everybody gets lost.
Yeah.
Thank you. Any more comments? Well, if not, let's thank Professor Lia del Moral. Now we're gonna take the picture here, so please stay there. The workshop picture. Now, please, everybody come here. In the coffee break, we will also have a cake after, and the coffee break's not now, but just announcing. So come to see Chico blowing the candles. But now I have this picture here. Please come. Pode ficar sentada. Se quiser, não. Come. Who's take the pictures? Photographer. Here. Você pode ficar também, não tem?